Anyway, yeah, I know. Now that we've crapped on people's haircuts in the classroom, let's learn some math, right? Good Lord. It's just never a dull moment. It's never a dull moment. Anyway, Unit 1.5, let's call it B because there's going to be a third day of lesson. So I'll call that one 1.5C on YouTube or whatever. Here's part B. Well, you know what? Recap of part A. What did we do yesterday? Yesterday, we relearned, because this is not new knowledge, that complex solutions always come in conjugate pairs, as well as irrational solutions always come in conjugate pairs. We said any polynomial of odd degree will have at least one real zero, where 3 is the smallest odd degree one. And what we did at the very end was we took the solutions of 2, 2, and negative 3 plus 1, knowing that means negative 3 minus 1 is also a solution. We rebuilt this fourth degree polynomial, this quartic. And we sketched the graph. We used our graphing calculators to find our maximum and our minimum values. There's another minimum. And then we just said up, decreasing, increasing, decreasing, increasing. That's all we did yesterday, okay? Now, boop, without graphing technology, today we are going to be factoring polynomials. The first two are very interesting because we're going to factor them over the complex numbers. That means when I factor them, I don't even need to have nice, pretty results. I just need to make sure that none of my x's have exponents any longer. We have a third degree polynomial with 4 terms. And if you remember back to Algebra 2, you have the rational root test, which is, remember, the P over Q stuff with synthetic division and the long list of guess and checks until you could get something fully factored. Well, that's what you have to do if you have 4 terms, unless it factors by grouping. Good news, everyone. This one factors by grouping. Will we have to get to the whole P over Q and all that stuff? Yeah, eventually, I believe so, I think. But for now, factoring by grouping. So how do we factor by grouping? Artificially group the first 2 things and the last 2 things, like that. And we will look at these 2 groups independent from one another. So let's look at this first group, this x to the third minus 3x squared. We're looking for the GCF of this first group. So you're just asking yourself, what do those 2 things have in common? What's the biggest thing that I could take from both of them? X squared, that's it. All right, so here's what we have. We have f of x equals, I got an x squared and a set of parentheses. When I divide out the x squared, because that's what factoring is, it's division. When I divide out the x squared, I'm left with x minus 3. Awesome. In order for factoring by grouping to work, you must be able to pull a GCF out of both groups, and you need the remaining stuff to match. So now you look at the next green group. What is the only thing that I could divide both an x and a negative 3 by? 1. That's it. And if you divide those 2 things by 1, you get, thank goodness, x minus 3 again. If these 2 things I wrote in black didn't match, you would not be able to factor by grouping, and you'd be forced to use rational root theorem, P over Q, synthetic division, Descartes' rule of sign maybe, but we don't have to, grouping. Treat this, because it is held together with multiplication, as one big object. Treat this, because it is held together with multiplication, as another big object. And then ask yourself, the things that I underlined in orange, what do they have in common? Because that is the new GCF. Hopefully it's obvious. They both have x minus 3 in parentheses. Now when I divide the x minus 3 away from the first orange group, it leaves behind x squared. When I divide the second orange group by x minus 3, it leaves behind plus 1. We have successfully factored by grouping. And there it is. But this is not fully factored because there's an exponent on this x. We have 2 options here. We could either, and actually the directions say to find all the zeros, so we can already see that one of the answers is positive 3. In order to finish factoring this, we could either treat this as the difference of two squares, like I did yesterday, and just get imaginary numbers, or set this equal to 0 and solve for x and use that to write your factors. And it doesn't matter which way you choose. They're exactly the same amount of work, exactly the same mathematics. But I get the feeling that more people will be comfortable solving this for x. So we'll do it that way. Subtract 1 from both sides. And then cancel your square with a square root, never forgetting that if you cancel a square with the square root, it creates a plus or minus. So x equals plus or minus the square root of -1. And what is the square root of -1, class? I. There it is. And from here in orange, I can see that the solution here is x equals 3, because that's what makes the inside equal 0. Hey, look, 1, 2, 3 solutions to a cubic. Remember what the fundamental theorem of algebra tells us? Whatever the degree of the polynomial is, that's how many solutions there are. We found all 3 of them. So here's your 3 solutions. But we're not finished, though, because the directions do say to factor it over the complex numbers. That means break it down into all of its individual pieces. That means this green thing needs to be broken into 2 sets of parentheses. So we'll write it in black. That way you know that it's part of this thing I circled in black. It's the answers. We have x minus 3, and we have x minus the solution positive I, and x minus the solution negative I. And there it is. So this is factored over the complex numbers. These are the 3 solutions. This is what we would say factored over the real numbers, because hopefully we all know the difference, the sum of 2 squares doesn't factor. It requires you to dip into imaginary numbers to make it work. So this is factored over the real numbers. This is factored over the complex numbers. These are the solutions. So we just have to be aware of what the instructions are telling us to do. Questions on this question, factoring by grouping, solving for these imaginaries, anything like that. Anything at all. Okay. Then we'll move on. See, it's just algebra 2. Nothing new. Let's do it again. Man, I hope it factors by grouping. It does. Did it have to? No, it didn't. But you see, we don't have a whole lot of space. So P over Q and synthetic division and all that stuff and testing values, really not a lot of space for it. This does factor by grouping. Okay. Let's go ahead and handle that. What's the very first thing you should always look for when you're factoring though? A GCF. Yep. And this one happens to have one. It's not a very large GCF. It doesn't simplify it much, but there is one. That GCF happens to be the number 2. So I can factor a 2 off of the entire polynomial. You get 2x to the third plus 5x squared plus 8x plus 20. Remember I told you the only way that something will factor by grouping is after you pull your GCFs if the 2 sets of parentheses match. So that's how you can tell quickly if something's going to work or not. Like right here, I'm hoping that you're going to see no matter what you do, this is going to be a 2 and this is going to be a 5 because they have nothing in common, right? What's the biggest thing you could divide 8 and 20 by? 4. And if you divide by 4, you get a 2 and a 5 again. So that's the check that yes, factoring by grouping will work. So exact same thing I did before. Throw some green parentheses on there to artificially group. Making sure to always capture this middle symbol. Reason why. If this was a minus sign, in fact, if anything you're factoring begins with a minus sign, you have a negative GCF. Okay? Always, always, always. First green group. The only thing they have in common, just like last time, x squared. Factoring off the x squared from this blue stuff is going to leave me 2x plus 5. You all already told me what I can divide away from 8x and 20. You said it was 4. Dividing out the 4 gets me 2x plus 5. Since the stuff in purple matches, factoring by grouping works.
How rare is it for it to actually end up like factor by grouping working? Because it feels like it's like very situational.
It is very situational. Factoring by grouping is one of those things that you hope works, because if it does, it's a shortcut. But unless a question was specifically designed to make it work, it doesn't.
For right now, is all the questions we're going to do mostly a factorable by grouping?
For right now, until we've reviewed rational root theorem, if I ask you to factor something and I don't give you any more knowledge, then yes, you're going to have to factor by grouping. But when you get to questions like this one, where grouping doesn't work, you have to use the other knowledge that's given to you in the question.
Okay.
You might have noticed that I didn't bother reading this to you.
Yeah.
And that's because we can see quite easily, just with a quick check, that grouping will work. And that's why I didn't bother talking about this yet. But in this question, I won't have a choice because grouping won't work. Okay. So let's go ahead and finish up grouping. We've got the 2 on the outside. We're going to factor away the purple 2x plus 5 from both things. And it'll leave behind the green stuff only, an x squared and a plus 4. This does say to factor over the complex numbers. Just like before, we could take this x squared plus 4, just like I did here with this x squared plus 1, and we can solve for x. Get you x squared is negative 4. You take the square root of both sides. You remember that anytime you cancel a square with a square root, you've created a plus or minus on the other side. And the square root of negative 4 is 2i. Hey, look. They already told me positive 2i was one of my solutions. Oh, look. Its conjugate negative 2i was the other solution. I could have started with that knowledge. I could have started by saying, since 2i is one of my solutions, so is negative 2i. I then could have taken my 2i and negative 2i and rebuilt the quadratic that produces those, and then done long division with it to get the 2x plus 5. But we're happy we didn't have to do that because, well, long division takes more time than factoring by grouping. But we now know how to break this apart. We got the 2 on the front. That does not produce a solution because there's no x there. We got a 2x plus 5, which produces our only real solution. And then we've got x minus positive 2i, x minus negative 2i. We have factored over the complex numbers. 2 of our solutions are here. The third solution comes from here. Subtracting 5 from both sides gets you 2x equals negative 5. And then dividing both sides by 2 gets you x equals negative 5 over 2. Decimal sucks, so I'm going to keep it as a fraction. So those are our 3 solutions to our cubic. This is its linear factorization over the complex numbers. Linear because none of the x's have exponents. And this is 100% review from what you learned in Algebra 2. Not a new thing has happened yet. Would you like to ask me any questions about that one? For this one, we have another polynomial with 4 terms, and I'm hoping you can see really fast that the GCF up the front here would leave a 3x minus 1, and there is no way that becomes a 3x minus 1. So we can see that fast that factoring by grouping will not work. You have a question for me?
I just realized the question I had.
Oh, about the last one. Okay, what's up, Sage?
Just about like what would the actual answer be? Would the answer be that f of x equals 2 times the 3 different?
Well, this has 2 different answers. The directions were find the remaining zeros. So here's all 3 zeros.
Okay.
Factor over the complex numbers. Here's the factoring over the complex numbers.
Okay,
So just this one's asking for all of it, yes. Because this doesn't factor by grouping, we are forced to use given knowledge. We were told that x equals 1 is one of the solutions. This one does not say factor over the complex numbers. It says factor over the real numbers. Just so we're clear on this, this is factored over the real numbers. This is factored over the real numbers. X squared plus 4 and x squared plus 1 are what we call irreducible quadratics. They're quadratics who have either irrational or complex solutions. We say irreducible. It's the same thing as saying that doesn't factor. So this question says, write it as a product of linear and irreducible quadratic factors. This is a linear factor. This is an irreducible quadratic. This is a linear factor. This is an irreducible quadratic. So it's asking us to get it in this format. Don't get it into the complex numbers. So it makes it sound like the quadratic that's left over after this is going to have complex solutions. And the only way to get those is the quadratic formula. But we would need that quadratic first, wouldn't we? We were told x equals 1 is a solution. If x equals 1 is a solution, x minus 1 is a factor of f of x. And if something is a factor, that means you could divide without getting a remainder. Now, there are 2 types of polynomial division. There's one type that works in very special situations, and there's one type that always works. My former students already know that I'm going to go with the method that always works. I don't like trying to memorize niche crap if I don't have to. So what method of polynomial division always works? Long division. Could I use synthetic division here? Yes, it could. But that's because I know under what circumstances synthetic division works. Particularly when you're dividing by something linear, you could use synthetic division. But I prefer long division. We're going to divide this polynomial by x minus 1 using long division. The one thing you have to remember when doing polynomial division, and it doesn't matter if it's long or synthetic, is you cannot have any gaps in the powers of your polynomial. They must count down from highest to lowest with no gaps. X to the 3, 2, 1, none. This was not missing any powers of x. But let's just say it didn't have an x there. Let's just say that this was the whole polynomial. It would go x to the 3, 2, none. Missing my x to the 1s. If it's missing that term, you have to fill it in with a plus 0x. If it's missing the x squared, it's a plus 0x squared, so on and so forth. Anytime you're missing an x term, you have to put it there with the plus 0x with the right exponent. No gap teeth smiles. Can't have any gaps in this grill, okay? You got to have all the teeth accounted for. I want to see all the chiclets. All right, there they are. So here they all are. Now, long division. What we're trying to do is we're trying to make the front of the divisor match the front of the dividend. We do that using multiplication. So what do I have to multiply x by to get 3x to the third? 3x squared. And that 3x squared then goes on top. And I like my like terms to line up, so I'm going to write it above the x terms, the x squared term. Now, just like regular long division with numbers, you take whatever you have here and you multiply it to this. But it's going to require a distribution. So I take this 3x squared and I distribute it to the x minus 1. Mr. M, how do I know if I missed a gapped tooth? How do I know if I missed a term? Very simple. When you go to your subtractions, your like terms won't line up. If your like terms don't line up, that means you missed a 0 somewhere. Go back and start over. Big old minus, big old equals. Notice that I did not put this as a tiny minus sign in front of that 3. That's because I'm trying to remind myself, no, I'm doing this black stuff minus the green stuff. And I point when I do the subtractions. And because my like terms line up, I don't need to see the x's. I don't say the x's, excuse me. I don't need to say them. 3 minus 3, yep, that's 0. Good, I needed that to say 0. Negative 1 minus negative 3. Be careful. Minus negative means plus. So this is negative 1 plus 3. 2x squared. I was always taught to drop down one thing, so I'm only going to drop down one thing. When would you drop down more? If you wanted to, I guess. Or if you were dividing by something that had 3 terms. If you're dividing by something that has 3 terms, when it stacks up, you want to be able to subtract 3 terms from 3 terms. So then I would have dropped down one more, just so that I always have the number of, see how I had 2 green objects? So I subtracted down 2. If this had said like x squared plus x minus 1, I would have 3 things and I would have subtracted down. And you always want to make sure that you have the right number of things to line up. That's it. Just make sure you have the right number of things lining up. Just like before though. Oh, that was supposed to be in black. Darn it. There. I need this x through multiplication to become a 2x squared. How do I do that? What am I multiplying x by to get 2x squared? 2x. A couple people are whispering it. There it is. So take that 2x. Oh, I forgot to drop down my 7 minus 7x. Take that 2x and distribute it to the x minus 1. 2x times x is 2x squared. Look, like terms, lining up. 2x times negative 1, negative 2x, like terms, lining up. Big, obvious, ugly minus sign. Like terms lined up, so I don't need to say the x's. 2 minus 2 is 0. Good. It needed to be 0. Negative 7 minus negative 2. Remember, minus negative is plus. This is negative 7 plus 2. Negative 5x. And lastly, throwing the purple pin by accident, dropping the plus 5, and then asking yourself, what would I multiply an x by to get minus 5x? I hope everybody sees that it's negative 5. Good. And just to prove a point, take that negative 5 and distribute it. You distribute this negative 5, and what you get is negative 5x plus 5. And anytime you subtract something from itself, you will be left with 0. So see, I had no remainder. Why? Because x minus 1 was a factor. That happens when you divide by a factor, you get no remainders. The directions have led me to believe that this is the irreducible quadratic, meaning this would have complex solutions, meaning it wouldn't factor, right? Just a quick double check. 3 times negative 5 is negative 15. Are there 2 numbers that multiply to negative 15 that add to 2? Oh, there are. 5 and negative 3, actually. This factors. So you have to factor this. Now, I don't know what method of factoring you like, what method of factoring you've practiced, what method of factoring you are good with. I don't care either. Have one and be good at it. I'm going to show you how I factor. I know it's going to be 2 sets of parentheses. I know the 2 front terms multiply to a 3x squared. That forces one of them to be a 3x and the other to be an x. I know the back numbers, multiply to negative 5. That means I have a positive and a negative. I have a 1 and a 5. Now, which symbol goes where and which number goes where? I don't know. Time to guess and check. Let's say this is a 1 plus 1, and this is a negative 5. Negative 15 plus 1, not 2. What if this is a negative 1 and this is a plus 5? 15 minus 1, not 2. This can't be the 1. It must be the 5. That makes this the 1. Now I just have to know which one's plus and which one's minus. 3 times negative 1 is negative 3 plus 5. Yep, there it is. And if you don't understand what I did, then use the Lizzie method, or slip and slide method, or supercross method, or the AC method. I don't care. Have a method for factoring. You've been factoring since Algebra 1. Be good at it, please. Okay? There it is. Whoa! X minus 1 showed up again. So not only is x minus 1 one of the factors, it's a repeated factor. Here's our linear factorization. The 3x plus 5 and a pair of x minus 1s. So what does that tell us about the graph? What's going on at x equals 1? A bounce. My graph is bouncing. And since it's a positive leading coefficient, I know this graph has an average rate of change that is positive. That means this graph looks like this. It crosses at negative 5/3, which is almost negative 2. It bounces at positive 1. And it has a positive average rate of change. It looks like that. Guaranteed. Ta-da. I even know where that y-intercept is. It's 5. We know a lot about that graph now. Did the directions ask for that? No, but it's great review. Cool. Questions on that one?
I'm just a little confused on the actual factor that you did right at the end of 3x plus 5.
How I factored, you mean?
Yeah, like when you figured out the 5 and the 1, how did you figure that out?
A lot of guess and check. So 3 times negative 5 is negative 15. And I knew that there were two numbers that multiply to negative 15 that add to 2. The fact that there are two numbers tells me I can factor this. I didn't use the two numbers. I just said I know it's factorable. So how is it possible that I multiply two things, get a 3x squared? One of them is a 3x and one of them is an x, because 3 is prime. How is it possible to multiply two things, get a negative 5? One thing is positive, one thing is negative. And since 5 is prime, one is a 1 and the other is a 5. So I just had to guess and check the combinations of pluses, minuses, 1s, and 5s until I saw that the addition in the middle added to 2. If you don't know how to do that, and there's a good chance you don't, do one of the methods that you were taught. The AC method, which ends up being a style of factor by grouping, the Lizzie method, the slip and slide method, the supercross method, and wherever other method your teachers might have used name-wise, have a method and be good at it. Okay? It doesn't matter which one you use. This is like a speedy form of guess and check. So this graph has no complex solutions. It's 3 real solutions. More Algebra 2, please. Symmetry. Symmetry. I need to get a tiny piece of scrap paper, because what I did in period 7 will not show up on the camera. So in order to pull it off, I'll have to draw it. That way it's on the camera. Boop. Okay. So what's up with symmetry? The terms even and odd, they describe symmetry that exists for graphs of a function. Are there other types of symmetry? Yes, but algebraically what we really care about is even symmetry and odd symmetry. Okay, so I'll read the definitions, we'll talk about what it means, and then I'll draw what it looks like. Okay. An even function. A function f is even if and only if when the point x comma y is on the graph, then the point negative x comma y is on the graph. Okay, what does that say? That says if you switch the symbol on x, it did nothing to y. That's what that says. Switching the symbol on x does nothing to y. Cool? Okay. Geometrically, reflecting over the y-axis doesn't change anything at all. Algebraically, everywhere you had an x, you plug in a negative x. You do all the simplifications. If the result is the same function you started with, then it's even. Graphically, I'm going to use letters instead of shapes, okay? I'm going to use the letter capital B. That's a horrible capital B. Jesus, where did I learn how to write? I'm going to draw a big blue 3. That's what it looks like. Notice that over here the x's are positive, yes? This is the y-axis. Reflecting over the y-axis should get me back the exact same picture, only mirror imaged. Because if you look right here, if let's say that was x equals 1, I got the exact same stuff going on when x was negative 1. What it says is, if you change the symbol of the x, the y values stay exactly the same. That's what even symmetry looks like. The y-axis acts like the line of reflection. Cool with that idea?
Yeah.
Awesome. A function f is odd if and only if when the point x comma y is on our graph, then the point negative x comma negative y is also on the graph. Okay, what this says is, if you change the sign on the x's, it'll change the sign on the y's. That's what that says. Geometrically, reflecting over the y-axis is the exact same thing as if you had reflected over the x-axis. See how important transformations are? Algebraically, if you take your original function and you replace all of your x's with negative x's, then you clean it up. If the result looks like all you did was multiply by negative 1, then it's odd. And lastly, graphically. I'm going to do my best not to screw this up. A capital B. That's a little bit better. Now that I'm under pressure, I forgot how to write B for some strange reason. Pay no attention to the man behind the curtain. This will be right back. That is how you recognize oddly symmetric. If you turn this picture upside down, this blue B, well, this B would be down here, yes? And there would be a different, and there would also exist a B up here, yes? Okay, but what if you turned it left, right? There'd be one here from there, and this one would go there. Oh, the same thing. And one other way you could recognize it, if you could spin the graph a half circle around the origin and get the exact same picture, then it's odd. I mean, I know the colors don't match, but other than that, It's the exact same picture. Cool with all that? Boom. All right. So let's look at these pictures. Our options are even, odd, neither. You have one of three things to say, even, odd, neither. I'm asking all 28 of you to have an opinion, even, odd, or neither. Class, what kind of symmetry does this have?
Odd.
This has odd symmetry. You know how I recognize it as odd symmetry? Because if I turn it upside down, it's the exact same image. All oddly symmetric functions must be able to be spun around the origin. If you can't do that spin around 0, 0, it is not an odd function. Also, you could see that you have this coordinate right here at 1, 2, right? Its corresponding coordinate is at, 1, -2. Its corresponding coordinate is at -1, +2. Look what happens when you change the symbol on the x. It changes the symbol on the y. So change this thing's symbol, changes that thing's symbol. Ta-da! Okay? So this has odd symmetry. Again, I'm looking for 28 opinions. You have 3 options. Those options are even, odd, or neither. Class, what kind of symmetry does this have?
Even.
This one is even. And the reason why is because the y-axis is acting as a mirror. The left and right sides are the exact same picture, just mirror images of each other, just like that. Where it didn't matter if x was positive or negative, you were going to get the same y value. All evenly symmetric functions, I was going to write symmetric, all evenly symmetric functions have a axis of symmetry on the y-axis. Cool with that? And looking for 28 opinions, class, even, odd, or neither?
Neither.
Neither. Yeah, there's nothing going on here. Neither even nor odd symmetry going on there. So that's how you recognize it graphically. What about algebraically? My Algebra 2 students are struggling real bad right now with this exact concept. They have a test tomorrow, and this is on their test tomorrow. Testing for even, odd, and neither. Look, both tests begin the same way. Plug in negative x and check out the results. So let us do that. Pretend each one of these says f of x equals. So for the first one, what we're going to do is plug in negative x. Everywhere we had an x, I'll open a set of parentheses. And I'll drop in negative x. And now it's time to clean it up according to the order of operations. What is negative x times negative x going to get me? Positive x squared. But here this just says minus x. And this just says minus 12. Are this function and this function exactly the same in every way? No, not even. Now the only thing to do is check for odd. We're going to compare negative f of x to this result, which is right there. If negative f of x matches this result, then it's odd. Let's go ahead and see what we get if we take our f of x and multiply by negative 1. That means distributing negative 1 across the entire thing. Gets me negative x squared minus x plus 12. Are these two results exactly the same in every way? No. Then it's not odd. That means this one has neither even nor odd symmetry. Great. Now I knew that before I did any work. And it's because I have accidentally memorized a pattern. Memorizing patterns is not how you are successful in this program. But nonetheless, when I finish this box, I will tell you the things that I've accidentally memorized. Never purposefully memorized these facts that I'm going to tell you. Okay? Let's do it again. Remember, it says f of x equals. Both tests start the same way. Replace all your x's with negative x's. Then you have to clean it up according to the order of operations. An odd number of negatives is always going to get me a negative result. An odd number of negatives will get me a negative result. And if I multiply two negatives, I get a positive here. Clearly not the same as f of x. So not even. But then we compared this result to what would we have gotten if we just multiplied by negative 1? So we wrap the whole thing in a set of parentheses. We throw a negative 1 on the outside. We distribute to see what we get. Gets me negative x to the 5th plus 4x to the 3rd. Oh my gosh. Plugging in negative x is identical to if I had just multiplied by negative 1. That makes this odd. These two are exactly the same, so it is odd. I knew that was odd before we did any work because I have accidentally memorized some patterns. And the last one, without doing any work, I can tell you is even because I've accidentally memorized some patterns. But let's prove a point. Everywhere my f of x has an x, I will open a set of parentheses. And that's where I will throw in a negative x. And simplify that according to the order of operations. But an even number of negatives will always give you back a positive. And this even number of negatives, also a positive times negative 6. Oh my gosh, it looks like I did absolutely nothing. Because it looks like I did absolutely nothing, I know this is even. So, secrets, tricks of the trade. Here they are. Your guys are packing up. That's unfortunate. In order for a polynomial, and it must be a polynomial. These things I'm telling you are only for polynomials. In order for a polynomial to be odd, every term must have an x, and every exponent has to be odd. In order for a polynomial to be even, every exponent must be even. Notice I didn't say every term had to have an x though, because if I stuck like a +3 on the end of this, it's still an even function. So in order to be even, every exponent must be even. In order to be odd, every term must have an x with an odd exponent. Armed with that knowledge, even, odd, or neither, odd, because every term has an x and every exponent is odd. No work even needs to be done. I don't suggest you try to memorize those patterns. I suggest you go through this work so many stinking times that they're obvious to you. One day you'll get there, nerds.